Without further ado, we're going to talk about the fundamental chemistry of the 3D printing resins. We're going to focus on vat polymerization because that seems to be the most prolific. And we're going to talk about the components, what goes into it. We're going to talk about a lot of basic chemistry. And how does the resin change from liquid to solid? I mean, it's a primary issue that we're faced with, but yet the mechanism is not necessarily very well known. How to incorporate 3D printing in your laboratory. How does the printer work? You all have access to a variety of different printers, but yet understanding how it works may help you choose and grow your laboratory. Why do the parts need to be washed after printed? Some of the basic stuff. And also, what does the light box do? And then the limitless potential for 3D printing. So as I talk, we're going to cover a number of different topics. If you have any questions, just raise your hand, and Eric there will hand you the microphone, because I'm old and I need a little assistance. Okay. Okay, so first, let's talk about materials. Let's talk about where we are with the resins versus what the traditional materials were. So we have metals. Now, metals solidify in a regular pattern. One on top of the other, they're in a regular pattern. And surrounding them are electrons. The electrons are the are the basic for the bonding of the materials, in all materials. But in metals, it's a unique situation because the electrons are covering the entire thing. And there's the metal atoms, the gold atom or the palladium atom or the cobalt atom, they're sitting there surrounded by electrons. So when we put a force against those materials, when we put a force against the gold, let's say, it'll resist it to a certain degree, but then it'll start to move. You say, okay, fine, I'm surrounded by my electrons. I'm going to take some electrons with me as I move, as I deform. And we can see where the where the alloys are under the engineering alloys. I'm sorry, that's a little out of focus. But you can see lead, as you know, is a very soft material. So you put a pressure on it, it'll resist it to a certain degree, and then it'll start to flow. And it'll keep flowing because the materials, because the electrons are surrounding the atoms, and it'll just keep going until it reaches a certain point, and then it'll finally break. Now, where that point is and how much stress you have to apply depends upon the nature of the atom. For example, I have here lead, aluminum, and steels. So lead, as you know, is very soft, so you could push it a little bit, but it'll elongate a lot. And the same thing with aluminum. It'll resist it more than the lead did, and the steel will resist it even higher. But it'll always deform. That's called ductility. And you have that ductility because these materials are surrounded by electrons. Now, the next item are ceramics. Now look at the structure of the ceramics. It's very defined. Not only is it very defined, but the electrons are also very defined in which way they can go. So you have a blue atom, and the electrons are surrounding the blue atom, and that electron can only go from the metal atom to the oxygen atom. And it only goes in one direction. And the oxygen atom says, hey, I'll give you another electron, but you have to give me back another electron. So it goes back and forth, but it's only in one direction. So what does that mean to the properties of the material? That means that you could put a lot of force against the ceramic, but once you put too much force on it, it's going to break. No ductility whatsoever. And those are illustrated all the way up in the corner where it says engineering ceramics. That's where our zirconia is. So for zirconia, or any ceramic, but in our case we're talking about zirconia, you could put a pressure on it until a lot of pressure, and then it'll break. For our alloys, you could put a lot of pressure against it, but instead of breaking, it's going to first deform, and then it'll break. However, these materials have no structure to them. It's a random, no defined structure to them. It's a random structure. How they connect is totally random. And sometimes some of the materials don't connect at all, and we're going to talk about that. Okay, that's okay. You can sit there. Okay. So here, for molecular materials, we're talking about something that's very, very low in strength. As a matter of fact, they're below the woods. So would you want your teeth made out of balsa wood? I don't think so. But that's what we're making out of these resins. Okay. Now, I tried to make this as non-commercial as possible. So what I did, I went out and I got the information from Niche. Now, Niche does not make resins, does not make printers. They make testing materials. They make testing machinery. So they make the machinery that's used, the instrumentation that's used to test the resins. Now, what do they say about the resins? Number one, photopolymers, that's what those resins are called. Photopolymers are thermosets. Thermosets are highly cross-linked. In other words, in order to join together, that's what that word means, cross-linked. That's how they join together, okay? And they're giant macromolecules. We're gonna talk about that in a minute. Strong covalent bonds between the materials instead of hydrogen bonding, as you normally have, like within oil, you have hydrogen bonding. Okay. Liquid components are mixed and solid state is reached through curing as you apply the UV light. Okay. They're not reversible. You take your water bottle, it's made out of polyethylene. That material, you could crush it, recycle it, make another polyethylene out of it. As a matter of fact, that's how they make the water bottle to begin with. They make a little stump about that big, and then they blow it where air, and that gives you the bottle itself. And you could go back and forth, back and forth. You could remelt it, you could reform it. Not these materials. These materials are a one-way street. It's a one-way street. They're more brittle than the thermoplastics. The polyethylene would be considered a thermoplastic. The 3D resins are considered thermosets, and they're substantially more brittle. The cross-linking results in a higher TG. TG is the gelation temperature. So at what point do they become gelled? Okay, that's important because we have to control that reaction. In order to go from liquid to solid, it has to go through that gel state. And that gel state sometimes causes problems, and we're going to talk about that. Okay? And they're very resistant to solvents. That's why we have to wash the parts, and we'll talk more about that too. Okay? And we're talking about light curing, UV light curing in particular, and they give examples like the acrylates, epoxies, polyurethane, and we're going to be concerned about the acrylates. Okay. Now, one more. So what are the advantages of vat polymerization? Vat polymerization, you can use a wide variety of materials. A lot of these materials can be made to be UV curable. And you see that even in the hobby industry. You have a lot of things you can make out of them. You can make your own Legos, okay? Very good accuracy, and we're going to talk about how that is generated. Smooth surface finishes, highly detailed structures, fairly thin wall thicknesses, if you wish, and the machine build volumes, the volumes that they're talking about here, 40 or 50 centimeters, those are for selective laser applications. That's what the laser, that was the older technology, SLA, and that was one of the first technologies that came into our industry and is being replaced by other vat polymerization processes that we're going to talk about, okay? Now, the disadvantages, you need support structures. And the support structures are made out of the same build material. That may be an advantage in some cases, but in most cases, they don't like to see that, okay? And purely UV curable systems are brittle, and they change properties over the lifetime of the products. You can see that yourself when you print a model or when you print a bite splint. If you keep it there for a long period of time, it may discolor. It may actually change shape after some time, depending upon the resin. Okay. So what do these things consist of? They consist of something called a monomer, and we're going to talk about the words, okay, that controls the viscosity of the printing resin and aids in the structure of the solid polymer, okay? And then another thing called an oligomer. Okay? And again, we're going to talk about the words in a minute. This produces, the oligomer itself produces the backbone of the solid polymer. So you need the oligomer in there, and the monomer is there to ensure that the polymer is going to be combined together, okay? And then a photoinitiator. This is the most important part of the whole thing, and it makes the whole thing work. So this is a material that gets added in very small percentages, but it's very effective. When the UV light hits it, it breaks apart. It creates something called a radical. It's not important to understand the words as much as it is the operation, okay? Now that free radical goes out to the monomer and says, hey, I have an electron for you. The monomer says, hey, okay, fine, I'm gonna use that, and it breaks apart a bond, which we're going to talk about, and that makes the material cross-linked. Okay, again, we're going to talk about it in another way. So for dental applications, we're talking about methacrylate chemistry, and all of everything that you see out there are based upon the same type of chemistry, the acrylates. Why? Because the acrylates are biocompatible, and they've actually been used for many decades, and we're gonna talk about that as well. They have low water absorption, which is very important because you have to put this in your mouth, and you want to make sure that there's not going to be any bacterial growth. Okay. And they have what's called adequate mechanical properties for low-stress dental applications. Okay. Okay, now, everything starts with polymethyl methacrylate. Polymethyl methacrylate was invented in Germany in 1902, and it was used initially as a bone cement. It was used in dentures, and during World War I, it was used as a cranial plate. So when you had part of your skull broken, they would actually pack it with this polymethacrylate mush, and it has to be very biocompatible to be next to your brain and still not cause a problem. Okay? And now we make plexiglass out of it. So you can think about the hockey players hitting against the plexiglass. They're attempting to damage their brain as well. Okay. Okay. Now I want to point out one thing. This is the chemical structure of polymethyl methacrylate. And look at that thing that's in the bracket. That's the mer part. And you see that little N? That means there are many of those parts. Okay? Many, many, many. So that's the one structure, and that structure, when it's polymerized, when it's solid, that one structure gets attached to each other over and over and over again. Okay. Now let's talk about some of the words. Okay. Monomer. Mono means one, and mer means a thing. That's it. It's that simple. So we're talking about, in the case of polymethyl methacrylate, the one thing is this structure here. Boom. Now, the polymer, or the oligomer, the poly means many, and so does oli in a Greek. It means many, and the mer is again a thing. So with the polymer, we have the same thing just over and over and over again. It repeats. Okay? So the reaction starts, you have this liquid in the vat, you hit it with UV light, the UV light to the initiator breaks apart, and that initiator creates a radical. That's what I have there as R. And then that propagates. So the radical goes against the monomer and says, hey, I'm going to break your bonds together. I'm going to break your bonds, and you're going to reform new bonds. And that monomer says, okay, fine. And then that creates another radical that goes out to another monomer and says, hey, I'm going to break your bonds, and you're going to reform your bonds. And they say, okay, okay. So again, you got over and over and over and over again until finally there's nothing left to bond to. And that's your solid. So this reaction, what does that mean? That this is one molecule. This is one molecule. One drop of water, okay, everybody knows what water is, right? H2O, okay? You have the hydrogen, oxygen, hydrogen. Okay, that's it. That's one molecule of water. How many molecules of water are in one drop of water? Anybody want to guess? Come on. 1,000? Million? Sextillion. Sextillion. I love that word. Sextillion. It's a 1 with 21 zeros behind it. Okay. 21 zeros. That's how many molecules are in one drop of water. Now, how many molecules are in this printed model? Anybody want to guess? 1. That's right. This is one big giant molecule. That's why they're called macromolecules. And in our case, they're called actually giant macromolecules. This is just one molecule because it's the same thing, that mer, that's was added together over and over and over again. And it just keeps going. And that's it. One molecule. You could think of it as joining Legos. Legos also have 2 spots in order to connect them, just like the methacrylate we saw. We saw it had 2 spots. Again, you add them together. And if you did it randomly, like you see some of these are connected randomly, that would be like the structure of what we're looking at. Now, where did this stuff come from? We're talking about, okay.
I was going to say, what's happening to the radicals as they're being broken apart?
It just keeps the one radical breaks apart. That's one atom of what was added. Okay, so the photopolymer, the photoinitiator is added. There are multiple atoms of these. Okay. And multiple molecules of these. And each one will then gets hit with the UV. As each one gets hit with the UV, it breaks apart, forms a radical, and that radical will then connect to another monomer. And it just keeps going on and on and on until it's saturated and there's no more left. Sometimes we have to put in more than one type of photoinitiator, and we're going to talk about that as well. And sometimes only one. All right, but we'll get into that in a little bit. Now, so what is the source of all of this stuff? Dinosaur remnants. These poor creatures died in order for us to make 3D resins. 2 kilograms of petroleum is needed to make 1 kilogram of PMMA. So it's not a very efficient process, but it's there. So this is the methacrylate setup, and that's the methyl. So that makes methyl methacrylate, okay? That's it. Now, doing this operation is not new. We did this starting in the 60s with composites, the composites that replaced amalgam. It's the same thing. It's the same type of reaction. You go in there with a light and you zap it. There was a photoinitiator in there, and that made that liquid that was put into the cavity solid. The problem is it shrinks. And for restorations, the material shrinkage was compensated for by adding fillers, silica, sometimes alumina, and we're seeing some of the resins that are trying to do the same thing, adding zirconia to it. Okay, so these materials, again, the operation itself is not new, but instead of doing it in small quantities, now we're doing it in larger quantities. Okay, same type of chemistry. Now the chemical companies have recognized this, and they're saying, hey, okay, we need to modify these materials in order to improve the properties of the materials. And that's what's happening. We have a lot of chemical companies like Ron, for example, or Herkel. They were originally satisfied with just selling the chemicals and then you do what you want with them. Now they're saying, hey, this application, this 3D printing application, is a big deal. We have to get involved in this. And they're working with a variety of companies, and they're saying, okay, fine, what do you need? And when we tell them what we need, then they come back and they say, okay, we have a resin for that. Or we'll make a new resin. We'll make a new resin in order to improve it. Okay. Now, 3D printers have the same issue with regard to shrinkage. It's not as much because, again, we've had some new materials to add. And where do we compensate for that? In the material file. So each resin has a material file, and this happens to be one for a SIGA, and the scaling factor you can see is up there, 1.006. Okay? So just like for zirconia, you put in the scaling factor in order to do the milling. For the 3D printer, the manufacturer of the resin has to calculate what that shrinkage is, and then that has to be added to your material file. So what does that mean for you? That means that when you change resins, if you have one printer, like in a SIGA printer, it's open. When you change resins, you have to make sure you have the material file that goes with that resin. Okay, okay, now how do you know what's in this stuff? Well, in the United States, you're going to get an SDS sheet that looks like this. And it doesn't tell you anything. What's really in there are these things here. Triacrylates, bis-DMA, a whole bunch of different diacrylates. Now you see the diacrylate? Di means two, and that means it has two connection points. So that little bit of liquid can be hit with the radical on either side, okay? And then you see here, there's our triacrylates. That means there are three places. And when you have this type of a mixture, what happens is the random structure, no, I'm not at that point yet, but the random structure sometimes blocks some of these things off. And I'm going to get to that. One of the things, this is one of the things I want to impress upon you is the importance of the safety data sheet. You have to read the safety data sheet. I know you may not be used to that because you're dealing with zirconia, which is quite inert, or alloys, which are also quite inert. But this is a mouth guard. And the mouth guard is made out of the methacrylate and then a triacrylate. So the majority of it, like 80% of it, is the first chemical, and almost 20% of it is the 19 or 18% is the last chemical. And then it has some titanium dioxide in there. That's what makes it color. The titanium oxide is a very, very, very fine material, but that's what carries the color. So when you see gray, when you see pink, it's titanium oxide in there in different forms. And it enables us to add color to the resin, because the resins are naturally, the polymethyl methacrylate are naturally clear and naturally colorless. Okay? And then there's this other thing there called TPO. That is the photoinitiator. It's a phosphine oxide. Now, that material will, if you ingested it, will actually may affect your fertility. It's quite potent. Okay? And that's what's on the right side. So it tells you, number one, this material is considered hazardous. Now you're making a mouth guard. You're going to put something hazardous in the patient's mouth? No, because after the polymerization, then it becomes biocompatible. But the components that go into it are not biocompatible. So we're taking something that's toxic and we're making it into something that's tolerated by the human system. You have to recognize this when you're fabricating these materials in your laboratory. Your people have to be protected. Now, you have to read it. Skin irritation, number one problem. You could be allergic to these things, and if you see a skin irritation is seen sometimes, actually the person just touches it, and the whole arm will just be totally red. And you have to get them out of that area, okay? Eye irritation is especially important. If this thing splashes in your eye, you go directly to urgent care, the emergency room, okay? Carcinogenity, that's that TPO. Okay? And toxic to reproduction, that's the TPO as well. Now, the probability of ingesting that is very low, I would hope. You know, when no one's googling these things, okay? Okay. Okay. It's extremely important for you to be concerned about the correct protection for your people. So you see here, protection against the clothes with an apron, gloves, critical. Gloves are critical no matter what operation you're talking about. Whether you're talking about pouring the stuff in the vat, whether you're talking about taking the material out, washing it, or even in the cure box. Gloves, important. Now, this is a nice picture, but what is wrong with this picture? This person does not have one part of PPE that they need. Hair, right, exactly. You don't want to put your hair in there, nor do you want the hair to go into the model. I mean, it'll look weird, but anyway. So yeah, you need a hair net. Need a hair net. Okay. Now again, for vat polymerization, we have good resolution, good accuracy, good surface finish, and for the printers that we're talking about, relatively quick to build. The disadvantages, no matter what we do, these parts are going to be somewhat brittle. I'm going to have to change that after a while because one of the things we're looking at is printing some of these denture materials. And the denture materials, we compare them to the original dental materials, like the Lucitone, for example. You go out and buy Lucitone and traditionally make a partial and test it, and then take the digital print and test that. The digital print is actually better than the traditional way of doing it. So in this case, we got a little bit of better results. Okay, supports are needed. Solvent cleaning is required. Post curing is required. It's critical that you post cure, and it's critical that you post cure correctly. Reading the instructions has never been more important than with these materials. And they're generally moisture and UV sensitive, of course. Okay. Now, how do we know what's in the container? Well, you buy this instrument called FTIR, Fourier Transfer Infrared, and all you're doing, all it does is you take a sample, and it could be a liquid or a solid sample, and you reflect infrared against it. And what happens is you get this pattern. Okay. Now on the right side, I have the chemical. Here's the BIS-GMA. That's a urethane methacrylate. That's a very popular material. These two are very, very popular for adding. TG-DMA. That's also very popular. And then two minor ones. But look at the ends of these. Okay. You see this dashed line, there's 2 lines here. Traditionally carbon is not shown on these diagrams, but that's a double carbon bond. And that's where the photoinitiator attacks. So you can see on this one, on the bis GMA, it has 2 places to attack. On the UDMA, it has 2 places to attack. They're a little offset, but they're 2 places. The TG has 2 places again, and then the other ones on top are only 1 place. When the infrared light hits it, it generates a pattern, and each of these bonds will react to the pattern in a different way. So you could distinguish between the chemicals by looking at the pattern. Okay? Now we're going to have a little audience participation. Okay. I'm not going to call it a test because then everyone will leave. Anyway. So here, let's look at the UDMA. UDMA, what's unique about this material? This hump here, close to, it's actually 1535. Between 1550 and 1500, it has that large hump, right? And then what about the bis GMA? The bis GMA has a little lump at the just before 1600. See, and the others don't. The others don't. So you take these patterns and you look at them, and you put them in the machine. You put the material in the machine. You run the pattern, and then you compare the pattern to your library of previous patterns that you have. So you could take the material and actually dissect it and determine what's there. And here we have three different combinations. They all do the same thing. However, the 3 manufacturers had 3 different approaches to it. Okay. Now, what do we see on the bottom one? We see that hump. So what do we know what's in there? We know that is the UDMA, right? We saw that before, and it's only there. And look at this the little peak up on top, on the green one. That's bis GMA. So that little nudge up there, closest just before 1600, that's bis GMA. And the middle one has a little bit of bis GMA and none of the UDMA. So by looking at it, using this instrument, we could actually tell the chemical components of the material. Okay. We could also do something else that's shown by the lighter lines on all 3 cases. We can measure the degree of polymerization. The degree of polymerization is how many of these little bonds have we broken and reformed in order to make it cross-linked, in order to make it solid. Okay? So by looking at the difference between the first run and the last run, we could see, like on this one here, on the red one, you see there's a much greater, it's almost at 2/10 at this time, at this wavelength. But the last one that we ran, you see it's lower. That peak is lower, and it's the same thing for all of the other ones as well. And notice one thing: they're all tending to the same pattern. And why is that? Because we want the same material. This is the same application. So 3 manufacturers came up with 3 different ways of making something, but at the end, after it was cured, they're all the same. They're all chemically the same. And none of them go to full reaction. So what does that mean? That means there's going to be some free monomer in there. We can't have that because that monomer is reactive to your skin. So you have to do something to get rid of it. Okay. Now, why did it happen that way? Because the material itself is a random structure. So in that random structure, some of the ends get left behind because they get blocked off. They can no longer cross-link with another monomer or another oligomer. They can't cross-link because they're blocked off. It's a 3-dimensional structure, and they just can't get in there anymore. So even though you have a photoinitiator in there that may still be active, that little bit that's left is never going to come out. some of the composites that are used for dental fillings, they only have a reaction of like 65%. So we're doing fairly well when we get up to like 80%. But that means we have to get rid of the material that's there. Okay. Now, this is a formula for a very popular resin for temporary crowns. So I'm going to go through the formula, and we're going to see what each component does. Now, some of these have more than one use, but I'm going to talk about the major use. Okay? So what does it consist of? It consists of monomers and oligomers. It says encapped. That means, what does that mean? That means it's attached to a methacrylate group. One thing about chemistry, they'll find different ways of saying the same thing. It's a form of obfuscation because they don't want someone else to copy the same formula. Okay. Okay. First, the first one up is actually the one of the most important ones, oxalic acid. That's a stabilizer. You'll know when you look at the bottle, it'll say the period of use, it will be a year or 2 years. Okay. That's important because that's not going to be active after that period of time. So you have to keep track of your inventory. Okay. Okay, so we already talked about the dimethacrylates and then the urethane methacrylates. That's the UDMA. Now we add a dimethacrylate here, the sex one, the 1,6. That improves the viscosity of the material. These things are generally, they start off like molasses, and you know when you put it in the printer, it has to be flowable. So we have to add something in order to make that flowable, okay? And then there's another material, hydroxyethyl methacrylate, that improves the surface adhesion. So you want that material, once it's solid, to stick to the plate. And that's one material. Here we have the phosphine oxide again. This is the TPO. It's generally added 1 to 2%. And then we have another BAPO with another phosphine oxide. That's a little less toxic, but again, that's again as a photoinitiator. And then we have this HPMA in there, which adds more sites for it to link to. So we're hoping to get actually less of that residual material and make the reaction go to completion. Okay. Now, this is a very popular material for making temporary crowns. It works very, very well. You can see it has a lot of materials in there, and it took the manufacturer some time in order to develop it, a couple of years. And it works very well for temporary materials. Okay. And as I mentioned before, there are 2 different photoinitiators. Why do you want 2 photoinitiators? Because the wavelength of your printer determines how effective that photoinitiator is going to be. So here we have the TPO and the BAPO, and we can see that the TPO is very active at 385, and the BAPO is a little more active at 405, and those are the 2 main UV wavelengths that we use. 405 was originally used for a lot of the hobbyists, and then 385 came in more for the medical applications. Okay, as I said, this is a one-way street. We have to cross-link it, we have to get it from solid to liquid to solid, and we're done. That's it. Modifying the viscosity of the resin. Most of the resins that are used for vat polymerization are between 150 and 1,000. Water is 1, and molasses is 10,000. So that's like a figure of merit for you there. Okay. Now, do the resins need to be mixed before use? That's a question asked by a lot of people. Do I have to keep this thing on the hot dog roller? And the answer is maybe. It depends on how much effort the manufacturer went in order to stabilize that sileic acid or the titanium dioxide. These are colloidal pieces, which the colloid is like salt in water. That's a perfect colloid because it's transparent. Milk is a less perfect colloid, but there's little fat particles in there, and you could take it to the extreme. A long time ago, you actually had cream inside the milk. Not anymore. That's gone. But that was an example of a colloid where you get separation. And in our case, we do get separation if we don't take care in either the manufacture of it, or in some cases the manufacturer will actually tell you, no, you have to mix this before you use it. And if they tell you you have to mix it before you use it, do that, or else you're going to waste a lot of time. Okay, now incorporating 3D printing in your laboratory. This is not a commercial. I just want to show you there are two different types of printers. Okay? There's LCD and DLP. Those are two different technologies. Now we're going to talk about the technologies. Now notice one thing. You see where it says resolution? That's 49 microns, 62 microns, 49 microns, 50 microns, 56 microns. And I've added 2 or 3 new units here that are being introduced at this show. But does the resolution matter? Some people, I mean, when you talk to the salesperson, they're going to tell you that the resolution matters. Okay, but all of these will produce the same type of restoration consistently, independent of that factor. Now, what's your responsibility? Your responsibility is to make sure that that printer is calibrated. Here we have something that we were used to about 10 years ago in vat polymerization, where it was not accurate and not reproducible. Nowadays, we can get something that's repeatable, but when it's not in calibration, it's not accurate. And here we have what we desire, accuracy as well as reproducibility. So make a schedule for yourself as to when you're going to recalibrate these units, because whether you do it monthly or whether you do it biweekly or whether you do it weekly, it doesn't matter, but it's more important to do it consistently, because these things do go out of calibration. Okay, okay, we're going to talk about the different types now of printers. In general, the schematic is like this. You have a build plate, you have a vat. The bottom of the vat is UV transparent. That's generally Teflon film. It's fairly inexpensive Teflon film. And you have a projector on the bottom. That distinguishes between the two, and we're going to talk more about that. And then the liquid resin, and then the cured part. And then, of course, we know we need a support material in there. Now, how the Z-axis is controlled is very important. But the manufacturers can choose different ways of doing it. The simplest way is to just assume that the material is going to be there, and you just raise it and lower it by a fixed amount every time. That's it. You put in the 50 microns, and every time it's going to go up and down 50 microns. So it's going to go down, go in there, going to flash, and then raise it up, and then come back down. When it comes back down, it's going to move it by 50 microns. Okay? There's another way of doing it, and that is to put sensors on the bottom of the film plate, and those sensors will actually measure the resistance of the liquid as it hits the build plate. And so, some printers have this, and it gives you a much better result that's going to be more consistent. Okay. Now, for the LCD printer, the LCD printer uses an LCD screen, the same type of screen as you have on your televisions. Okay. It's a liquid crystal display, and behind the liquid crystal display are LEDs that are UV LEDs that shine through it. Okay. Now, how it develops a pattern, as you know, for the two types, LCD and DLP, we're talking about the entire layer flashes all at once. So how does that work? For each of the little pixels, the current is either on or off. If the current is on, the light goes through. The current is off, the light gets blocked. That crystal is actually physically moving. Now, for a DLP printer, now this is a newer development, and it costs a little more because the components cost more. In most of the DLPs, they have that center that I was talking about, so you get a little more accuracy on the z-axis. And now you have a projector that goes into a lens that goes against the mirror. But it's not just a regular mirror. This is the heart of the DLP. This is a digital light processing chip that was developed by Texas Instrument. And what we have here is really a marvel of technology. There are on the 4K chips. Most companies don't need 4K chips right now, so they're a little less than that. But on the 4K chips, there are like 8 million little mirrors. Most of the ones that say they're 4K, it's actually 4,000. It's actually 4 million items rather than 8 million mirrors. But it's a little marvel because all you're doing is directing the light. So when you have the light, when you want the light to go to the vat, the mirror goes one direction. If you don't want that particular pixel on, the mirror just moves the light to another area, which doesn't hit the top of the vat, or the bottom of the vat, I should say. So that mirror does the entire thing all at once, the one layer all at once, and those little mirrors, or 8 million mirrors or 4 million mirrors, whatever it is, depending on the chip that the manufacturer uses, are instantaneous, because all they're doing is creating an electrostatic charge on one side and not on the other, so the mirror tilts. Okay. Now, which one is better? So go to Google Scholar, type in LCD versus DLP printing, the differences, and bingo, you're going to get a whole bunch of articles, 10,000 results. And what those articles are going to say is that for dental applications, they're all the same. All of them are adequate. So we're not making electronic components, we're not making space components, we're making dental components, and especially on the model. If you go back 30 years, the model was the standard. You had a gold coping on top of that model, and the margin didn't fit. The metal didn't meet the margin. You pulled the gold down to the margin because you knew that model was the accurate representation of what's in that patient's mouth. Now, with digital, the restoration is more accurate than the model. So if we're printing models, okay. Now, why do we need to wash the parts? This is actually, I took this in our model room. What we have are two vats of IPA, and they vibrate. They just move back and forth. That's it. That's a very simple approach, very effective approach, and very cost-effective approach as well. Now, why do we need two? We need two because the outer surface of the liquid, the outer surface of the model that we printed is always unreacted material, and these materials are very resistant to any type of solvents. IPA is the best one to use because you can recycle it. Okay, so you need the two because you're going to get the first one off, and then there's going to be another one right behind it, and you need to clean it the second time. And if you notice, the first vat is much thicker than the second vat. has more material in it than the second batch, but you still need that second vat. And the ones you could buy have 2 wash stations, and again, you're going to find the same thing. Make sure you change the IPA out on a regular basis, because as you use that alcohol, the alcohol itself is not going to be as effective against the parts over time. Okay. And again, the IPA can be reclaimed. If you're using a lot of IPA, buy the little reclaim unit. You'll save yourself money, and you don't have anything to throw away. Okay. Now, what does the light box do? Well, I keep saying that this stuff doesn't go to completion, and we've documented that it doesn't go to completion. So we have to do something to make sure that that surface is totally polymerized. The reaction is exothermic, which means it generates heat. So when you put it in the light box, as I said before, each light box has its own energy source. It has its own energy source, and that source is going to vary. So sometimes some resins will tell you to put in for 200 flashes or 5 minutes. Other times you'll get one that says 2,000 flashes, and then you flip it over and do it again. Just realize that as you do those flashing, you're generating heat. So you have to make sure you don't overdo it, okay? And the manufacturer of the resin will tell you exactly what the minimum number is, and what's also the maximum number. I want you to consider that to be the maximum number as well as the minimum number, okay? Now, sometimes, most times you should use nitrogen in these boxes, because the nitrogen displaces the oxygen. Oxygen will stop the reaction dead from happening, so you'll always wind up with some extra on there, and you don't want that. So you use nitrogen in the curing box, it'll remove the oxygen, and again, you have a better result. Okay, and we can make a lot of things with these vat polymerizations. Okay, and we have, as you know, soft splint, hard splint, temporaries, denture bases, impression trays, ortho models, stone models, and clear aligners, even thermoforms for clear aligners. Okay. Now, I wanted to share this with you because it is typical of an R&D project. Okay. So first, you have a technology trigger. Either somebody develops a patent, or a patent goes completion, and other people jump into the marketplace. Okay, and initially, in our case, we had something called 3D printed permanent crowns. Okay, these materials are not permanent, like zirconia is permanent, or like alloys are permanent, or feldspathic porcelain is permanent. These are not permanent. One of the reasons why they're not permanent is because there's always some water solubility left in the material, and when you have that in your mouth, it's going to get into that part, and that's going to generate something that you may not want to keep in your mouth for a while. Yes?
Should we be giving our dentists expiration dates for the items that we're giving them that are made through the 3D process and process?
Well, I don't know if we have enough information to even tell you what that is. Some companies out there will tell you, "Oh, we've had studies for 2 years," and that's correct. Studies for 2 years, and the wear rate is not significant. Other people will tell you 5 years, okay, but no one will tell you 30 years because they haven't been around that long. So I guess the answer is I don't know. We don't know yet. We don't have enough information to give a number. But the way I look at it, all of the stuff we're printing, temporary. That's the way I look at it. Okay, that just makes it simple. Yes.
Does this apply to the metals that are?
No, I can't hear that. Okay.
Turn this slide on, please. And Paul, we're at 2 o'clock. I know you had.
Yeah.
It was at the beginning.
Yeah. Okay.
So does this same thing apply to the metals that are 3D printed? I've seen a few of those partial pieces coming out.
Yeah, those partial pieces are not made of resin. I'm talking about things that are made of resin, not 3D printed. So it's the resin, it's the material that's the problem, not the operation. Okay. Okay. Yeah, this is the last slide. So anyway, we just go through inflated expectations and then disillusionment with the process, and then we get a slope of enlightenment. We say, oh, okay, we could do this, and then we have a plateau of productivity. And right now, making surgical guides, models, or lasers into crowns and bridges are there. Okay. Thank you for your attention and your patience. Okay.